Section 3.5b. Once again, in the second half of 3.5, we're going to look at some even numbered problems from the homework assignment, and then you'll have the odds to do for homework. So open up your books to page 234, beginning with problem 30. Population P in thousands. Now, when you're doing these problems, make sure you're paying close attention to how the variables are defined, especially the units that they are defined in. So in this case, the population P in thousands, which means that if P was 4, it would really represent 4,000 and so on. Population P in thousands of Las Vegas, Nevada can be modeled by that formula, where T is the year, with T equals 0 corresponding to 1990. So if T was equal to 5, we would be talking about 1995. If T was equal to 8, we would be talking about 1998, and so on. In 2000, the population was 478,000. Find the value K for the model, round your answer to 4 decimal places, then use the model to predict the population in 2010. So in this case, they are nice and they tell you that you have to find K first. A lot of times it's not going to tell you that. It's just going to say, go right to step B and say, use your model to predict the population in 2010. You have to understand that you always must know what that K value is first. So in this case, we have P equals 258 times E to the KT. We're told that in the year 2000, well, in the year 2000, T would be equal to 10. The population was 478,000. But remember, when we go to plug that in for P, P is already given in thousands, so we're going to plug in 478 for P equals 258 times E to the K times 10 power. From here, now we need to find that value of K. So I need to isolate the exponential. Once the exponential is isolated, now I take the natural log of both sides. Finish solving the equation for K. Natural log of 478 over 258, all divided by 10. K is equal to, plug that into your calculator, natural log, 478 divided by 258, divided by 10. We get a K value of 0.0617. There's our K value. So there's part A. Now part B asks us to find the population or predict the population in 2010. So go back to our original model, which is now E to the 0.0617 times T power 2010 is 20 years after 1990, so T is equal to 20. And now we plug that expression into our calculator. (258) E to the 0.0617 times 20 power. Population is 886.215. Remember, though, that is in thousands, so how many people does that really represent? It represents 886,215. There's the estimated or predicted population in 2010. Move on to problem 34. Depreciation. New laptop computer that sold for $1,150 in 2005 has a book value V of $550 after 2 years. Find a linear depreciation model for the laptop. So we need to write the linear equation based on the information that we're given here. Well, in this linear equation, normally in a linear equation, we think of X and Y. In this case, we're talking about time and the value of the computer for our X and Y variables. What ordered pairs are we given? Well, we know brand new, so after no time has passed, the computer sold for $1,150. And we know after 2 years that the computer was valued at only $550. Kind of nice here because this first point gives us the y-intercept. So all we need to do now to get our linear equation is find the slope between these 2 points. Slope, difference in y's, over difference in x's. We get a slope to be negative 300. Why is our slope negative here? Well, this computer is depreciating in value, or the value is going down as the years increase. That's why we get a negative slope. And our final formula in terms of the variables we picked here is the value of the computer will go down $300 per year, and the y-intercept starting at a value of $1,150. So there is our linear model. Part B, find an exponential depreciation model for the laptop. Round your numbers in the model to 4 decimal places. Okay, so let's go ahead and do that. Formula here is going to be the value at a certain time is equal to the initial amount times e to the kt. Plug in what we know. Once again, when we use an exponential model like this, you should know the first thing that we need to find is our k value. We know a value at a certain time is 550. We know the initial value is 1150. And we know that that has a value of $550 after 2 years. So now we're looking at this equation here that we need to solve for k. 550 over 1150 equals e to the 2k. Take the natural log of both sides. K is equal to the natural log of 550 over 1150, all divided by 2. Plug that into your calculator. At that k value, you're told to round the 4 decimal places, so negative 0.3688. There's our value of k. Once we find our value of k, go ahead and write your final equation. Value of the computer is going to equal that initial value, which was 1150, times e to the negative 0.3688 t power. There's our exponential model for this situation. C, use a graphing utility to graph the 2 models in the same viewing window. So let's take a look at these 2 equations in our calculator. Y equals, let's do the linear model first, negative 300x plus 1150. Second exponential model is 1150 times e to the negative 0.3688 x power. Now let's take a look at our window here and change this to the context of the problem. X, remember, is the number of years. So I don't need to look at negative years. Let's just go out 10 years. Y is the actual value of the computer. We don't need to go below 0 because it's not going to have a negative value. Maximum value we know is 1150. Let's spread our scale out to go by 100 so we don't have a bunch of marks there on our scale. If we look at that, there's our linear model. There is our exponential model. Part D then says, which model represents a greater depreciation rate in the first 2 years? Well, if we look at our table here, after 2 years, they both have the computer valued at $550. So they are the same as far as the depreciation in the first 2 years. Explain the advantages and disadvantages of each model to both the buyer and the seller. Well, if I look at this graph once again, according to this graph, when I look at the linear model, after 1, 2, 3, 4 years, the computer is going to have a negative value. Does that ever really happen? No, probably not. Again, computers do go out of date pretty quick. But even if you have an older computer, a lot of times you can sell it for parts, things like that. So it never really has a negative value. You don't have to usually pay somebody to take the computer from you. If we look at our exponential model, we know our exponential model here is going to get closer and closer and closer to a value of $0, which is more likely what happens over time. That computer does keep depreciating, but it again will always keep some value if it's not just for parts or whatever else it may be. So the exponential model overall is probably a better model. If we skip over to problem 42. Problem 42. Use the Richter scale from page 381 for measuring the magnitudes of earthquakes. Find the magnitude R of the following earthquakes of intensity. Let I of 0 be 1. Well, if we look at that page 381, actually that's the wrong page number. It's actually page 231. Our formula is R equals log base 10 of I over I of 0. But it tells us in the directions that I of 0 is essentially 1. So we just have that for our formula. Now, this is kind of an interesting problem because most people do not understand how earthquake intensity is measured. For instance, if you are told that on a certain day, an earthquake of on the Richter scale of 4.0 hit in California, and an earthquake hit in Japan on the Richter scale was measured at 8.0. So we have a 4.0 quake and an 8.0 quake. Most people are going to say, wow, the earthquake in Japan is twice as strong as the one that hit in California, but that is not the case because the Richter scale is based on a logarithmic scale. So as we take a look at some of these, first one in A has an intensity of 39,811,000. So when I go to plug that in, R equals log base 10 of 39,811,000. Plug that into your calculator. Log 39,811,000. And we get a Richter scale measurement of 7.6. Second one in B has an intensity of 12,589,000. So go ahead and plug that into our formula. Log base 10 of 12,589,000. Now, if we just look at the intensities here, we can see that the intensity in A, 39,000, is about 3 times as intense as this earthquake in B, an intensity of about 12 million to 39 million. So a little over 3 times as intense. Plug that into your calculator, though. And what's our Richter scale measurement? Well, we have log of 12,589,000. Hit enter, and you see on the Richter scale, that's going to be a 7.1 magnitude. So we can see on the Richter scale, when it differs by only a half a point here from a 7.6 to a 7.1, most people would say, oh, 7.6, 7.1, not much difference there. Is actually an increase of intensity of almost 3 times as intense as the earthquake in B. If we look at letter C, 251,200. Log base 10 of 251,200. Plug that into your calculator. You see that that Richter scale measure is 5.4. So you can see how measurements on the Richter scale can be misleading to the general public if they do not understand that this is a logarithmic reading. In other words, this is our value of r. That's the or the exponent that we would put on 10 each time to get the actual intensity of the earthquake. Problem 44. Use the following information for determining sound intensity. The level of sound beta in decibels with an intensity I is given by beta equals 10 log base 10 of I over I of 0, where I of 0 has an intensity of 10 to the negative 12th watts per square meter, corresponding roughly to the faintest sound that can be heard by the human ear. In exercises 43 and 44, find the level beta for each sound. So in 44, first of all, the formula we're going to be using here is beta equals 10 times log base 10 of I over I of 0, which they tell us is 10 to the negative 12th. So in letter A here, we're plugging in 10 to the negative 4th for I. So beta is 10 times log of 10 to the negative 4th over 10 to the negative 12th. Let's figure this out without using our calculators here and using what we know about exponents and logarithms. 10 to the negative 4th over 10 to the negative 12th. If I move that up, that 10 to the negative 12th up to the numerator, add those exponents, we get 10 to the 8th. Use your property of logarithms. Log base 10 of 10 to the 8th is just equal to 8. So we have 80 decibels for that sound intensity of 10 to the negative 4th. Letter B. Loud car horn is 10 to the negative 3rd watts per meter squared. Let's go ahead and find that. 10 log base 10, 10 to the negative 3rd over 10 to the negative 12th, which is 10 to the 9th. Use your property of logarithms. Log base 10 of 10 to the 9th is just 9. So our intensity there would be 90 decibels. Third one now, a siren from 30 meters away has a 10 to the negative 2nd intensity. So we have 10 log base 10 of 10 to the negative 2nd over 10 to the negative 12th. Use your property of exponents. Use your properties of logarithms. That's 10 times 10 or 100 decibels. So we can see by our intensity level goes up by a power of 10, our decibel level is as well. Last one here, problem 48. Application to science in the pH scale. Use the acidity model given by pH is equal to negative log base 10 of concentration of hydrogen, where the acidity pH is a measure of the hydrogen ion concentration H+, measured in moles of hydrogen per liter of solution. And 48. Compute the concentration of hydrogen for a solution in which the pH is 5.8. So looking at our formula, we're told that pH is equal to log base 10 of the concentration of hydrogen. We're told in problem 48 we want to find the concentration of hydrogen for a pH value of 5.8. So we're solving here for the concentration of hydrogen. It's a logarithmic equation. How do we solve a logarithmic equation? If there's logarithms on one side, we isolate the logarithm. That's already been done, and we change to an exponential. Base to the exponent equals the argument. Plug that now into your calculator. 10 raised to 5.8 power. I'm sorry, I need to go back here. I wrote the formula down wrong here. There should be a negative in front of here. So we need to back up a step here. We first need to divide by -1 to isolate that logarithm. And now change to an exponential. Base to the exponent equals the argument. Plug that into your calculator, 10 raised to the -5.8. Notice that is 10 to the -6, so we need to add 5 zeros out in front of this. And our concentration of hydrogen in this solution would be there's our 5 zeros, 1, 5, 8.